The title of this investigation is That's the Way the Ball Bounces. To conduct this experiment, we're going to need certain materials. This experiment, we're going to use several small balls. We'll need a piece of tape, a tape measure. We also need a wall, a hard, flat surface for the balls to bounce back from, and we need some type of either a phone or an iPad so that we can record the movement of the ball, because we want to see how much the ball bounces back from when it's dropped from various heights. Here's my setup for the experiment, and I'm going to drop a golf ball from 20 centimeters and see how much it bounces back, and then 40 centimeters, 60, 80, and 100 centimeters. And I'm going to see how much it bounces back, or to the height that it bounces back each time. To the height of the first bounce. Now what you might have noticed is it's really hard to tell what height it bounces back to on the screen. So I'm going to record it each time using slow motion on the phone, and that's why you need either the phone or the iPad so that you can slow it down, stop it, go back, and actually find the height. Using the slow motion feature of the camera, this is what the golf ball looked like when I dropped it from 60 centimeters. You can see that it rose about to the 48 centimeters. Here is the data table that I obtained when I dropped each of the 4 balls from an initial height of 20 centimeters, 40 centimeters, 60 centimeters, 80 centimeters, and 100 centimeters. In the table, it's the height that the ball returned to after the first bounce. So you can see there's some variation. What I'm going to do next to help us see the difference is I'm going to graph the data. In order to do that, I need to determine which is the x, or the independent variable, and which is the y, or the dependent variable. So I'm thinking the height after the first bounce depends on the starting height, so therefore my initial height or starting height is going to be my x, my independent variable, and the height after the first bounce is going to be my dependent variable, and that'll go along the y-axis. Here is my graph showing the results of the golf ball, and we can see that they lie more or less in a straight line. So I'm going to draw in the trend line, and I know that it should go through the origin, or through the point 0, 0, because when it has no initial height, it's going to have no height after the first bounce, because it's going to be on the ground. Here is my graph of the data for the golf ball. I drew in the trend line, and we know it's a proportional relationship, and it goes through the point 0, 0, because when it has no height, then it's not going to have a bounce. It stays on the ground. And here are the points that I selected to determine my slope from the line. Each square is representing 5 centimeters. So I went up 25 centimeters and across 30 centimeters. So my slope turns out to be 5/6, which as a decimal is 0.83. Now when I run my data through the calculator, I come up with the equation where A equals 0.83, which is my coefficient of A, coefficient of X, which is the slope, which is exactly the same as what I got on my trend line. And then I have B is negative 0.8. That is how much, well, a negative, it's a little bit below 0, of course, but it's 8/10 of a centimeter. or 8 millimeters. So that's really, really small. It's really close to 0. And my R is 0.999. So I have a very, very strong correlation with the golf ball. And the slope was 0.83. Because we're going to compare the slopes for the 4 different balls that were used. Here is my graph of my data for the tennis ball. I drew in the trend line already. Again, it's a proportional relationship and it should go through 0, 0. And then when I looked for the 2 points where the trend line is going to cross, where the x and the y values meet, so that my values are integers, I counted up and I have a rise of 20 centimeters, and across I went 35, so a slope of 20 over 35 reduces to a slope of 4/7, which as a decimal is 0.57. When I run this through the calculator, I came up with my coefficient of A, or my slope, as 0.575. My B is negative 0.7, and my R is 0.99988. So it's a very, very strong correlation. And I see that my slope on the calculator is very close to the slope that I got from my trend line. And the B is, again, it's 7 millimeters that it's off. It should have been 0, and I get a value of 7 millimeters. So again, it's very, very accurate. Here is my graph of the data for the pink Super Ball. And we notice that after I drew in the trend line, that to go from the points that I selected that are in pink, I rose 20, and then I went across 25, so my rise of 20 over 25 reduces to the fraction of 4/5, and it gives me the decimal of 0.8. And here on the calculator, I came up with the value for A, which is the slope of the line, is 0.82, and my value for B is -2. So the -2 for B is considerably larger than it was on the other 2 graphs. And that means I'm off by 2 centimeters. And when I look at my graph, I notice that, like right here, my data point is quite a ways from my trend line. So my points have a little bit more variation than they did with the other 2 balls that we looked at so far, which would explain why there's also more of a difference in the slope between the calculator and my trend line. It's just a little bit more inaccuracy. Here is my graph of the data for the squishy ball. And I drew in my trend line, having it go through the point 0, 0, and I found 2 places on the trend line that I can easily read the slope. So then I found that going from one to the other, I'm going to go up 25 centimeters, and then I'm going to go across 45 centimeters, which gives me a slope of 25 over 45, which reduces to 4/9, or a slope of 0.55. Using the calculator, I came up with A, the coefficient of the x term of the slope, as 0.555, and B is 0.1, which is 1 millimeter. So that's a very, very small amount for B. So it's very close to the 0 that it should be. But when I compare all 4 of the balls and the amount that they bounce back, their slope, what I found is that the squishy ball has the smallest slope. It's this one right here. And it is in fact very squishy. And the one with the highest slope is the golf ball, which is very rigid. The slope of the golf ball was very close to 1. It's 0.85. And a slope of 1 would be that when it bounced it, let's say I dropped it at 20 centimeters, the golf ball bounced back to 16 centimeters, but if it bounced back to 20, it would have a slope of 1, which means it would never stop. It would just keep from 20, it would go back up to 20, and it would never run out of energy, never stop, and it will continue forever. So the highest possible slope we could have would be 1. That would be a perfect return, and it would never stop. So the golf ball is really close to that. And that's what I want you to see, that this time, in this situation, we do have a maximum slope that can be achieved, and that would be a slope of 1. And that concludes this video. Thank you.